Welcome back to the deep dive. If you were to just stop 100 people on the street and ask them, what is a computer?
Hmm.
I bet almost all of them would point to the physical stuff. The aluminum case, the glowing screen, maybe the fan they can hear whirring.
Sure, they talk about the chips, the memory sticks, the wires,
Uh,
the things you can actually touch.
exactly. And, they're not wrong, but they're not seeing the whole picture either.
Well, that's it. That physical box is, of course, essential. But the sources we looked at for this really frame it as, well, as just the stage. It's the inert material waiting for the performance to start.
That's such a great way to put it, the stage. Because I think that focus on the physical box is probably the biggest obstacle to really understanding modern tech.
Uh-huh.
Because the real innovation, the genuine magic that makes a phone different from, say, a really complex mechanical clock, it's not just that it's faster.
Wow.
It's this underlying invisible idea, this concept that lets us build these unbelievably complex digital systems by just stacking simpler layers on top of each other.
And that foundational idea, the architecture that the whole digital world is built on, is abstraction.
Right.
And it's not just some fancy computer science term. It's the operational law of how things scale.
Yeah.
If you want to know why technology hasn't just collapsed under its own weight.
Yeah, why my phone can run millions of lines of code without me needing a PhD in electrical engineering.
That's it. You have to get your head around this one principle, abstraction.
Okay, so let's unpack that. Our mission for this deep dive is, I think, pretty straightforward, but also really powerful. We're trying to give you a shortcut.
Mm-hmm.
A shortcut to understanding how all this technology scales structurally. We're deliberately stepping away from the specifics, the programming languages or frameworks that change every year or so.
We're going for the bedrock, the things that don't change.
Exactly. We're focusing on the fundamental architectural layers that are basically constant.
And the sources we've reviewed for this, they really act as a blueprint for that. They map out this whole structure, this thing we can really call the digital ladder.
A digital ladder. I like that.
Yeah, and our job is just to guide you up that ladder, rung by rung, and show you what each layer does, why it's there, and the kind of incredible leverage it creates.
So before we start climbing, let's nail down a definition. What are we actually talking about with abstraction?
At its core, it's just the process of hiding details you don't need.
Hiding details.
Yeah, hiding unnecessary details so that you can focus only on what matters for the problem you're solving right now. It's funny, right? It's basically a deliberate practice of selective ignorance.
I love that. Selective ignorance. Okay, that makes sense, but it's still a bit abstract.
Of course. And that's why analogies are so useful here. The best one, the one the sources all kind of point to, is the car.
The car analogy.
It's perfect because it's physical, it's immediate, and everyone understands it.
So when you're driving a car, you interact with an interface, right? The gas pedal.
The accelerator, yep.
And its job is to simplify this huge, complex mechanical process down to one single action. Press down, go faster.
And crucially, the driver, the user in this case, is completely, totally abstracted away from what's happening under the hood.
Right. I mean, you're not thinking about the fuel injection timing, which is happening in milliseconds. You're not worrying about the pressure in the combustion chamber or the exact angle of the spark plugs.
Of course not. All of that complexity, the mechanical execution, it's all real. It has to work perfectly or the car just stops.
But the key insight, the thing that makes it abstraction, is that all that messy, complicated stuff sits neatly and functionally behind an interface.
The dashboard, the pedals,
Yeah.
the steering wheel, those are your interfaces. The engine, the transmission, those are the implementation details. Abstraction is just the boundary that separates them.
And once you get that, you see it everywhere. You realize that the computers, the entire digital universe is built on that exact same principle. It's just interfaces hiding details from the next layer up.
It's the engine of modern complexity management.
So let's start climbing.
Let's do it.
So we've got the general principle down. Now let's leave the car behind and get into the digital world. This is section 1. The layered architecture of computing.
Okay, so we're introducing this idea of the digital ladder. The core rule here is that technology scales by stacking these functional layers. Each layer is built to use the functions of the layer right below it.
Enter without needing to know how that lower layer actually does its job.
Exactly. It reminds me of building a house,
So?
Well, you pour a massive concrete foundation. And once that's set, the plumber who comes in to lay the pipes doesn't need to know the chemical formula for the concrete mix.
Right. They just trust that the foundation is a stable, reliable interface, I guess, for them to build on.
Precisely. And the sources really emphasize that this stacking gives you structure, but more importantly, it gives you protection
Protection from what?
from drowning in detail. The main goal of this whole architecture is to manage cognitive load, to keep your brain from having to process millions of things at once.
Drowning in detail? I mean, yeah. If every single software developer had to think about electrical resistance when they were writing a simple bit of code.
Nothing would ever get built.
Mm.
Innovation would just grind to a halt. Abstraction is the built-in system that makes sure we only have to think about what's necessary for the task at hand.
Okay, let's break it down then. Let's deconstruct this hierarchy, layer by layer, starting at the very, very bottom.
Level 1, physics. The absolute, undisputed physical foundation of everything.
So we're talking about literal reality.
We are. This is where the physical world even allows for the possibility of information. At this level, it's all about electrical currents. Electrons moving through silicon, mostly.
Right. Voltage levels, resistance, all that stuff from high school physics class.
That's it. It's pure matter and energy, governed by the laws of thermodynamics and electromagnetism. The whole digital stack rests on the simple, reliable fact that we can make electrons move.
It's the material reality. Okay, so what's one step up from that?
Level 2, logic gates. This is the first conceptual layer we build right on top of that physics.
Logic gates. So these take that kind of chaotic flow of electrons and start to give it some structure, some purpose.
Exactly. They harness it to make basic decisions. A logic gate is really just a tiny circuit made up of things called transistors.
And a transistor is basically an electronic switch, right? It can be on or off.
Precisely. An electrically controlled switch. And if you combine just a few of these switches in clever ways, you can create fundamental logical functions. The sources name the big three: AND, OR, and NOT.
Let's break that down because that's a huge leap right there. We're
Yeah.
going from just current to actual results.
It is a massive leap. An AND gate, for example, needs both of its inputs to be on, to have a high voltage, for its output to be on.
While an OR gate only needs one or the other.
Right, and NOT just flips the state. If the input is on, the output is off. And with just those simple building blocks, you've moved from passive electricity to active conditional processing.
So everything a computer does, from rendering a video game to running an AI, it's all just built from billions of these tiny little decision-making circuits.
In theory, yes. You can actually build what are called universal gates, like a NAND gate, which is not AND, and from that one type of gate, you can construct every other possible logical operation. It's computation built entirely on level 2.
Wow, okay. That foundation then leads us directly to level 3, binary.
Yes, and this is the critical move from physical reality current is flowing, or it's not, to symbolic representation, to actual information.
So the logic gates are physical switches. Binary just gives those states a name.
It gives them a symbol. A 1 might represent a high voltage state current is flowing, and a 0 represents a low voltage state.
So we've abstracted away the messy details of the physics. We don't care anymore if the voltage is exactly 4.8 volts or 5.1 volts.
We just care that it's a 1.
Yeah.
We've simplified reality down to a state of on or off, true or false, and now we can start to manipulate those symbols with math and logic.
And once we start stringing those zeros and ones together into longer sequences to represent numbers, letters, anything, we're ready for the next level up.
Level 4, machine instructions.
Okay, so if binary is the language, the letters, so to speak, then machine instructions are the grammar, the first actual words.
That's a great way to think about it. These are the specific low-level commands that the hardware, the CPU, is physically built to understand and execute.
This is what people call assembly language, right?
Essentially, yes, it's a human-readable representation of it. We're talking about extremely granular commands that are unique to a specific processor. Things like MOV to move a piece of data, or ADD to add 2 numbers, or JMP to jump to a different part of the program.
It's the machine's native tongue.
It is, and it's an incredibly difficult place for a human to work for any length of time. You're manually managing tiny little memory slots inside the CPU called registers. The sheer volume of instructions you need to write to do anything useful is just staggering.
To draw a circle on the screen, you'd be writing thousands of lines of this stuff, managing every single pixel by hand.
Which is exactly why the next layer of abstraction is an absolute necessity, not just a convenience. You simply can't build complex modern software at this level.
And that brings us, thankfully, to level 5, programming languages.
This is the layer that finally makes software development manageable for human beings. It's the abstraction built right on top of those machine instructions.
It moves us towards something we can actually read and understand.
Think about the difference. At level 4, to add two numbers, x and y, you might have to write, I don't know, 3, 4, 5 separate machine instructions.
Load X into this register, load Y into that one, run the ADD command, then move the result back into memory.
Right. But at level 5, in a high-level language like Python or Java, you just write z equals x plus y.
One line.
One line. And the programming language itself, through a program called a compiler or an interpreter, does all the hard work of translating your simple, readable command down into the dozens or hundreds of tiny machine instructions the CPU needs.
So the compiler is performing this massive act of hiding detail for you.
It is. It's your abstraction engine. And it's the first layer that's really designed for human efficiency and building things at scale.
Okay, so we're getting pretty high up the ladder now. Above the languages that are generating these instructions, what do we find?
We find level 6, the operating system, the OS.
The OS, the manager, the traffic cop, the resource coordinator for the whole machine?
That's it. It sits above the languages, and its main job is to manage how all the physical hardware, the memory, the CPU time, the disk space, is shared between all the different programs you're running.
And the main abstraction it provides is something called virtualization, right?
Yes, virtualization is key. Take memory, for example. The OS provides virtual memory. So when your calendar app runs, it thinks it has this nice, clean, continuous block of memory all to itself.
But in reality, that memory might be scattered all over the place physically or even temporarily stored on the hard drive.
And the app has no idea. The OS handles all that messy complexity, hiding the physical reality of memory allocation from the application. It does the same thing with the CPU, by the way.
The time slicing thing, making it look like your one CPU is running 20 things at once by switching between them hundreds of times a second.
Exactly. And it provides the gatekeeper, the system call interface. This is the formal, secure way that applications at the top layer can ask the OS to do something risky, like reading a file or accessing the network.
So it's the shielded door between my apps and the raw hardware.
Precisely. Which brings us to the very top of the ladder.
Level 7, applications.
The user interface, the part you actually see and touch. The calendar app, the spreadsheet, the video game. This is the layer that uses everything below it to create a useful, immediate experience.
So we did it. We climbed from invisible electrons at level 1 all the way up to an app icon on a screen at level 7.
And through that whole journey, that dual function of abstraction was at play. Every layer depends on the one below it.
But every layer also acts as a shield, hiding the overwhelming complexity of what's underneath. You can design your app at level 7 without ever having to think about the layout of logic gates at level 2.
And that is the engine of all modern technology.
Okay, so we've mapped the entire structure. Let's move into section 2 and talk about the real power of this, the benefits, the leverage that this whole system creates.
Leverage is absolutely the right word. Because this whole system is a ladder, every time someone invents a better, more efficient rung.
A better layer.
A better layer, exactly. It instantly provides this massive compounded benefit to every single layer built on top of it.
It's like compound interest for innovation.
That's a perfect analogy. Think about it. If you invent a super fast new database, that's a new improved layer sitting somewhere between, say, level 6 and 7, then immediately every application that uses it gets faster.
The financial apps, the social media apps, all of them. And their developers didn't have to rewrite a single line of their own code.
Nope, they just benefit automatically. The sources are really clear that this is the primary accelerator of progress in the digital world. You're always building on the successful work of the past, not constantly rebuilding the foundation.
Let's use a real example, the C programming language.
A fantastic example. Before C was invented in the 70s, a lot of important software, like operating systems, had to be written in assembly language, level 4.
Which we already said is incredibly tedious and difficult.
And it was tied to specific hardware. So C comes along as an improved level 5 abstraction. It's higher level, easier to read, but still gives you close control.
And because it abstracted away just enough of the machine-specific details,
it suddenly became possible to write a whole operating system, Unix, in a high-level language. This made the developers of Unix way more productive.
And then what happened?
Well, once you have Unix, a stable, powerful, portable level 6, it provides this incredible platform for application developers. So the innovation at level 5 led to a massive innovation at level 6, which then just opened the floodgates for countless level 7 applications that could now be easily moved between different computers. That's leverage. One improvement cascading all the way up the stack.
And that systemic advantage leads right into the second huge benefit, which is specialization.
Oh, absolutely. Abstraction is the only reason the tech industry's division of labor is even possible. It lets people become true masters of one narrow slice of that digital ladder.
Because without it, everyone would have to be an expert in everything from, I don't know, silicon doping to advanced cryptography.
It would be impossible. Let's take one of the examples from the sources. The calendar app developer.
Okay, so they're working entirely at level 7. They're thinking about user experience, time zones, notifications.
Right. High-level logic. They just assume that when they write a line of code that says save appointment, it will work. They are completely 100% abstracted away from the physics of silicon manufacturing at level 1.
The abstraction is so reliable that they can be a world-class expert on scheduling algorithms without knowing the first thing about photolithography or how a CPU manages its cache.
They're trusting the layers below them. The OS at level 6 guarantees the file will be saved. The programming language at level 5 guarantees the math is correct.
What about the other example, the data analyst?
Right. Someone running a huge query on a database with petabytes of information. They're using a language like SQL, which is another very high-level abstraction.
So they write a query asking to compare billions of rows of data.
And they get an answer in seconds. They have zero need to know how the OS is scheduling the CPU threads or how the kernel is managing memory page faults. Those are super complex level 6 functions. To the analyst, the query just runs. The how is hidden.
So the big insight for you, the listener, is that you actually gain your effectiveness by embracing the limited scope of your layer.
Yes, you can be incredibly productive at the application level precisely because you don't have to master the physics level. If you had to master all 7 at once, nobody would ever ship a product.
And that leads to the third benefit, right? Collaboration.
Fostering collaboration and iteration, because abstraction creates these sealed boundaries between teams. The interfaces, the APIs are like contracts.
An API, an application programming interface, it's like the official front door to a layer.
Exactly. So the team building the operating system can publish an API for drawing graphics. And the app developers know that if they use that API, a circle will appear on the screen.
Even if the OS team completely changes how they draw that circle behind the scenes.
That's the key. It allows for concurrent innovation. One team can be focused on making faster hardware, working at levels 1 through 4.
At the same time, another team can be improving the operating system at level 6.
And a third team is building better apps at level 7. And they can all innovate independently without breaking each other's work because they're all just talking to those stable, reliable interfaces.
So when the hardware team releases a new, faster chip,
The app developer doesn't have to rewrite their software. They just get a free performance boost.
yeah,
That decoupling is what allows technology to grow exponentially, not just linearly.
okay, we've really established that abstraction is this incredible engine for scale and efficiency. I mean, it sounds almost perfect. But there has to be a catch, right? If it's all about hiding details, aren't we just creating a generation of lazy engineers who don't understand the real costs?
That's a fantastic question, and it moves us perfectly into Section 3, the necessary trade-offs and risks.
The dark side of abstraction?
Well, maybe not the dark side, but the trade-off, definitely. The reality is you hide details for convenience, but that very act of hiding can obscure really serious problems.
So the goal isn't to just ignore the details forever.
No, absolutely not. That's the philosophical caveat. Persistent, willful ignorance is where the flaws and the vulnerabilities we see everywhere start to creep in.
So you gain speed and simplicity.
But you lose transparency and control. And that lack of transparency, while it's usually fine, it tends to show up in 2 major areas, performance and security.
And the irony is that the very architecture that's designed to protect us from the details is often the reason we can't see the detail when it really, really matters.
It's exactly. Let's talk about the first major trade-off. Some people call it the abstraction penalty. I like to call it performance surprises.
The abstraction penalty. Okay.
This is the price you pay for convenience. So imagine a developer working comfortably at a high level, say level 5, using some fancy programming library.
And they write a bit of code that looks perfectly clean and simple. Maybe it's one function call to copy a big chunk of data. To them, it looks like one step.
Right. But because the inner workings are hidden from them, they might not realize that when that one simple function gets translated down through the OS and into machine instructions, it's actually causing thousands of really inefficient operations.
Like what?
Well, Maybe it's repeatedly copying data back and forth in a way that is terrible for the CPU's cache. Or maybe it's forcing the operating system to constantly switch between different processes, which wastes a ton of CPU time.
And this is the classic, well, it worked fine on my machine problem, isn't it?
It is the absolute definition of it. On their powerful development machine, it seems fine. But the second that code gets deployed at scale, or on a device with fewer resources, that hidden computational cost, the abstraction penalty, suddenly becomes a performance catastrophe.
And the developer is completely blindsided because the abstraction layer masked the true cost of their choice.
Exactly. The only way to fix it is to break that abstraction barrier and go look at what's really happening underneath.
Which leads to the second, and I'd say far more dangerous, trade-off: security risks in the gaps.
Yes. Security vulnerabilities rarely live neatly inside one layer. They thrive in the gaps between the layers.
The handoff points.
Handoff points, exactly, where one layer's interface gives control or data to the layer below it. A classic example is a buffer overflow.
Okay, this happens at the boundary between the programming language level 5 and the raw memory management at level 4.
That's right. So in your high-level language, you might ask for a small space in memory, a buffer, to hold a username, for example. The abstraction makes this seem simple and safe.
But the language doesn't always rigorously check the size of the data you're trying to put in it.
And that's the failure. Because when it gets translated down to level 4, it's dealing with raw memory addresses. So if a malicious user inputs a username, that's way too long.
The extra data overflows out of its designated spot and spills into the adjacent memory.
Potentially overwriting other critical parts of the program, maybe even injecting the attacker's own code. And just like that, they've taken control of your application.
It's a perfect abstraction failure. The developer thought they were just handling a piece of text, but they were actually interacting with raw memory allocation, and the abstraction didn't protect them properly.
Or think about SQL injection. That happens at the boundary between the application code at level 5 and the database system at level 6.
The developer builds a login form. The abstraction makes it easy to take the user's input and send it to the database.
But if they don't clean that input properly before they hand it off, a malicious user can type database commands into the password field.
And the database at level 6 has no idea it's not supposed to be a command. It just sees instructions and it executes them.
And suddenly the attacker is dumping your entire user table. The vulnerability exists precisely in that gap, where the high-level layer made an assumption of safety that the lower-level layer didn't share.
And these things are so hard to spot because the whole point of the architecture is to hide that complexity.
Which brings us to the most important skill for you, the learner, to develop. Knowing when to zoom in.
You can't live at the bottom in the physics, but you also can't afford to be blissfully ignorant at the top when things go wrong.
The real difference between an amateur and an expert is knowing that the abstraction barrier isn't a wall, it's a door. And you have to know when to open it.
So if your app is suddenly running slow, the problem might not be in your level 7 code at all.
Right, the code might look perfect, but the actual problem could be deep down in the operating system's network stack at level 6. You have to have enough knowledge of the layers to know where to even start looking. You have to be willing to drop down and read the kernel logs.
Or, if a piece of your code is slower than you expect, you might need to zoom right past your high-level language at level 5 and look at the actual machine instructions the compiler generated at level 4.
You might discover the compiler made a bad assumption that's causing the CPU to work inefficiently. The point is, you have to choose the right level of detail for the problem you're solving.
Abstraction is your tool for everyday productivity, but a map of the layers is your tool for when things fail.
That's the key.
Wow. Okay, that was a complete architectural survey of the digital world, from literal electrons all the way up to the apps on our phones. Let's try and synthesize everything we've just covered.
Well, I think our findings are pretty definitive. Abstraction isn't just a feature. It's the non-negotiable architecture, the layered structure, and the engine of all modern digital scale.
It's what allows for specialization. It's what allows for that compounded innovation we talked about. It lets us build these unbelievably complex systems by breaking them into manageable parts.
And we've walked that whole stack, from level 1 physics to the level 7 UI. We've seen the incredible leverage you get when a better layer is invented.
But we've also seen the trade-offs, the hidden performance costs, the abstraction penalty, and the really subtle but dangerous security risks that hide in the gaps between the layers.
So you, the listener, you now have the foundational map. You have the architectural knowledge that powers everything digital around you. You know how it's all segmented and managed, And maybe more importantly, you know where the hidden costs are.
Which brings us back to that central piece of advice, the core takeaway from all of our sources for anyone who wants to really deepen their technical understanding.
It's simple, but it's powerful. If you genuinely want to understand technology on a deep level, stop memorizing tools first.
That's just a path of constant frustration, isn't it? The tools are always changing.
They are. Instead, learn the layers. Learn how they connect. Understand the architecture, the stack,
Yeah.
and you will understand both the power and the failure points of the entire digital world.
That structural map really does simplify everything. It gives you a framework to understand why some things succeed and others fail.
It turns chaos into order.
Okay, so let's end with a final provocative thought for you to explore, something that builds directly on the structure we've just mapped out.
Mm-hmm.
We started at the very bottom, at level 1, physics, electrons moving. Then we climbed one rung to level 2, logic gates, those physical circuits doing A and D, or R, and not.
The first moment of conditional processing.
Exactly. So my question is this. If this whole massive, powerful ladder of complexity is built on that physical foundation, what is the single smallest, most atomic unit of information that's required to make the entire stack even begin?
What's the profound leap?
Yeah, what is the profound leap that transforms a simple electrical current into meaningful computation?
It's the concept that the 0 and the 1 of the binary layer, level 3, are actually representing.
It's a deep question, I think. It asks you to think about that essential bridge between the physical world and the world of information. What is that single foundational concept that captures the simple existence of a choice, a state, a possibility?
Because that simple, smallest unit is where the true power of abstraction really begins.
Something for you to mull over as you start to see the layers and everything around you.